Hi guys, I am Rajababu. I am going to explain you in this video about a DCS, that is distributed control system. In our earlier videos we have discussed about various control systems based on Arduino, based on PLC, based on relay logic and many other things as well. So today we are going to see what is this DCS and why we need this DCS, what is the internal structure of this DCS, how it works and where it is going to be applied or where it is going to be implemented, and what is the role of this DCS in an industrial and other automation field. Hope this video will give you insight about a DCS and it will be more informative. Let us start with points to be discussed. What is control system? What are the types of control system? A definition of a DCS, architecture of a DCS. In the architecture, we are going to have various stages, that is operator station, engineering station, server, archiving system, automation system, and in automation system, we are going to have controller, HMI, input output modules, field devices, and finally we are going to have communication network, and where this DCS is going to be used, that will be in the application part. So let us start. What is a control system? Most probably you will be knowing what is control system. If a particular devices are connected together to achieve a particular task, will be called as control system. So it could be a very simple system or it could be very complicated system as well. For example, we have a fan in our home, which is a system which is used for cooling the room or cooling the place. What it has, we have a control switch and we have a regulator and we have the motor which is going to rotate the arms, and so that the cold wind or the cool wind is going to come out of from there. So how this system works? When we give the supply through the control switch, the regulator position will decide how much power will be given to the motor. So according to the input power availability to the motor is going to run, and based on that the wind blow or the wind velocity will be going to be decided, right? So in case if you have 5 different positions in the regulator, so the regulator will decide how much power at different stages. But there is no feedback in this particular control system. So you give a supply and it reaches to the motor and the motor rotates and it produces certain output. So the wind blow is there. But it doesn't give any feedback how much wind is produced. Is it enough for me to make the room cool? So this is a simple control system. It will be called as open loop control system. In case if you have AC in your home, that air conditioner in your home, you can see the same process. That cooling process is taking place here also. We have a control switch, and by operating this control switch, we are powering the air conditioner, and the air conditioner has various components. The major components are same like the fan. We have a motor which will be connected to the compressor system, and of course there are other few mechanical elements as well. And we have one more important component, that is called sensor. So which is going to sense the temperature of the room where you need to maintain the temperature, and you are going to set a temperature how much you need. Say for example, if it is a summer season and you want to maintain the temperature of 20 degrees in your room, so you are going to set the value using your remote or the manual control. Yeah, so 20 degrees you set it in the air conditioner, and the system what it is going to do is to continuously check the temperature in the room and the preset value. Compare these two values and it is going to take a decision whether the compressor should be in on condition or it will be in off condition. So in case if the room temperature is higher than the preset value, the compressor keep running. When you reach the temperature required by the particular person, so then the compressor goes off. So the difference between the fan and the air conditioner is that the air conditioner system, it has a sensor which senses the value continuously, and then it says whether the required temperature is achieved or not. But in the fan there is no such system. It is going to run and it is not going to check whether the room temperature is achieved as per our requirement or not. So these are two different examples of a control system. So a control system is a system that used to control the behavior of a device or process. It's a simple definition. And if you see this particular block diagram, it can be take an example of a fan. So where you give a input and we have a controller or a regulator, and then the fan itself, the motor, and based on this the motor produces the output. So there is no feedback whether the motor produces enough output or it is producing more or less, whatever it is. So if you see the second system, if you compare this first one and second one, you can see there is a new element called the sensor, that is a feedback element. So this feedback element should be given back. So when you have two signals, then there should be a element which is used for comparing these two. This comparison may be done with a controller, or it can be a simple comparator ICs if it is a very simple system. So you may have a comparator IC if it is a complicated system, and the data which needs to be compared, if it is complicated inputs, then you will have a complicated controller as well, or the controller will have this data to be compared, and then the controller will take a decision, and based on that the plant will, or the air conditioner will work, and it will produces the temperature reduction in the room. So again the feedback system gives whether it is achieved or not achieved. Based on that the process continues. So this is about a simple introduction about control system, open loop control system and a closed loop control system. And if you see the signal types what we have in the industry or in a day-to-day life, we can have two different type of signals. So where we have a discrete time signals and continuous time signals. This is very important to understand why we need a DCS. That's why I am going to explain about this as well. Discrete signals, you can see it is a sampled one. So one value to the another value, it is a sudden jump or a hike. It is not a continuous one. So at a particular intervals, we take samples. So this type of signals will be called as discrete time signals. And in continuous time signal, you can see it is infinite number of samples together will be called as continuous time signal. So at one point to another point, you have infinite number of sampling points. So you have very high amount of samples together in a continuous time signal. Say for example, if you see a temperature variation in a room, or a pressure variation in a process, or a flow variation in a process, so these data can be taken as a continuous time signal. So discrete time control system, based on the input what we have, the control system can be classified as a discrete time control system or continuous time control system. So discrete time control system deals with signals sampled at a specific time intervals, resulting in sequence of discrete values. So as like this one. So you have a discrete system where you have the samples and it is given to the discrete system and it produces the output. So mostly mathematical models include the difference equations for achieving this discrete time controls. And the next type of a control system is a continuous time control system. This system operates on signal that vary continuously over time, as I shown you in this picture, earlier picture. Both the input and output signals are continuous function of time. So engineers often describe continuous time control system using differential equations like this. Okay, so these are the examples of discrete and continuous time control system. So now let us start discussing about a distributed control system. So distributed control system is specially designed control system to manage complicated, giant and geographically distributed control system throughout the complete plant space. In this controller are distributed throughout the entire plant area. Say for example, you have a wide plant for wastewater treatment or oil refineries or any other power plants, something like that, where you have different locations which perform different tasks. So the controllers are distributed at a different areas, and those controllers perform the task which is near to that particular uh, machineries, and all these controllers are connected in a system where this all the controllers are performing, and we can monitor all of the work which is taking place at different areas, and we can control them, and you can archive them, and you can overall you can control the total process. These distributed controllers are connected to both the field devices and operating PC through high-speed communication network. Of course, when we have a different locations for performing different tasks with the different controllers, all these controllers are interconnected using a high-speed communication network. So if you see the centralized control system, say simple example, if you take a PLC based control system, say for example a folding machine or a welding machine or a drilling machine automations, something like that. So you will have a centralized processor, and it will have its own inputs, say 4 or 5 inputs from that particular machine, and based on the set points and the required points and the predefined program what we have in the centralized processing unit CPU, and it produces the output, and these outputs produces the required amount of automation in the output side. So this is a single process or a single unit which continuously do the function, but there are many different process together connected like this will be called as a distributed control system. Say for example, if you have 10 different PLCs performing 10 different process which may be interlinked or which may not be interlinked. So based on this output of a first PLC, this third PLC or fourth PLC will perform the next task. A simple example for centralized control system and distributed control system. So as I told you, in the distributed control system, we have different controllers at different stages, and it performs the task, and it is all interconnected in a high-speed communication network, and also can be monitored in an operator station. In case of any modification needed in the engineering station, from the engineering station you can do the modifications. And in the field control system also we have a HMI systems to monitor and reset the values or enter few new values. All these things can be done in the field control system as well. So this is a simple introduction for DCS, and let us see what are the components of a DCS. A distributed control system consists of several key components that work together to monitor and control the industrial process plant. These components includes controller, input-output modules, human-man interface or HMI, and communication networks. So this is it. So these are the few components. Though it has many components, I just give the highlights of the components. So this is the overall architecture of a distributed control system. It may vary. It's a simple sample only. It can vary for your own process and the plant. So it gives us an idea how the DCS looks like. So we have operator station which is located at different places, or it may be in a same place. The operator station is used to view the process at the plant at a different levels or different areas, and from there you can control the operation of the particular machines, and we can get the feedback charts and all those things in the operator station. So this is very important, where you are monitoring the whole plant, whether the process are going in a required way, or it is deviating somewhere, or we need to give some inputs to the particular controller. All those things is monitored here in the operator station, and these operator stations are connected with the Profinet. And the second level, we have servers, archiving computers, engineering stations, and in the third level we have the controllers. So these controllers are the one which is going to control the operation of a field devices. So these controllers are get connected with input devices and output devices using input output modules, and these input output modules can be having analog modules and digital modules and different other specific modules according to the devices which is get connected to this particular PLC or the controllers. So this level, the devices can be connected either using Profinet, fiber optic cables, or Ethernet CAT cables, or whatever the industrial communication method. So these are the internal components of this architecture of DCS. So let us see in detail few of them. So engineering station, operator station, and we have automation station. So we can divide it into three different stages. So in engineering station, what they do is they design the program, and they set all the values, and whatever the project software and the hardware configurations, everything is done in the engineering station. So you have, say for example, each controller has 20 or 30 inputs and 10 or 15 outputs. All these has many number of control loops. Okay, control loops, either it may be PID control loops or control loops according to the requirements. So these all control loops and the programs, hardware configuration, how it is get connected, all those things are done in the engineering station. In the operator station, we just watch what is happening actually in the plant. If any deviation is there, and we can interrupt them, and we can feed the required inputs, and also we can see graphically, like say for example, if oil refinery system, or water wastewater treatment plant and all those things, graphically you can see what is happening there, what is the temperature in the boiler, or what is the pressure inside the tank, or what is the water level in the tank, and how much flow is taking place from one motor to the another one, and all those things. So how much valve position, 50%, 30%, how much valve position is open. So all those things can be watched from the operator station, and the operator can control to certain extent to the field devices from here itself. Automation station, in the automation station, where you have the controllers, the controller, the controller which is going to control the field devices. So these controllers are going to receive the program and hardware settings from the engineering station, and it is going to get the inputs from the sensors and field devices through input output modules, and these input output modules gives the data, and this data is going to be received from these controllers, and these controllers is going to perform the task or perform the operation based on the inputs given from the engineering station, that is your code, PLC code, and then hardware settings, and different preset values and all those things. So based on that, it is going to produce the output, and the output also will be given to the field device through the input output module, and from this automation station we get the data to the server, archiving system, and operator station. So what is the liquid level, what is the temperature available there, how much valve is open, all these data are going to the engineering operator station, and also it is going to the server, and from the server it will go to the archiving system. So this is the different stations available in a distributed control system. So now we will see in one by one detailedly operator stations. So the operator station, as I told you earlier, it will show you graphically the total process at different areas. So you have five areas: area number 1, area number 2, area number 3, like that. And in each area you will have a process variables and the process which is taking place there. So for example, you have a water level monitoring system, or compressor monitoring system, or you have a valve positioning system, or different systems. So these all graphically will be shown in plant 1, plant 2, plant 3, like this, as shown in this picture. So it will show the exact values of the valve position, temperature, pressure, humidity, whatever the parameters which we need to monitor from there. Also, you can see it will give the alarms in case of any issues. It will give the alarms, so where you can reset the alarm, or you can change the values of the required temperature, pressure, or whatever it is. It gives the alarms and the indications as well. And it will also show the graphical data for various parameters, like say for example temperature, flow level, RPM, pressure, speed. All these data can be controlled from here. Parameters need to be controlled. So say for example oil refineries, so you need to know how much temperature should be maintained, how much flow and level, and so many other parameters which we need to control there. And trends, how the process taking place, trends graph, and alarms and warnings. All these data can be seen in the operator station, and based on that, you can control the process. The next one is server, and as I told you, these servers are getting input from the controller. So the controller is going to get the inputs from the field device, and it is going to perform the task, and based on the task it is going to give back the control signals and things like that to the field devices. And also at that particular stage, what are the data to be given back to the server. See, all these data will come to the server. From the server it will go to the operator station, and it will go to also archiving computers. So the purpose of this server is to collect data at the controller level, transfer data between controller and operator station. Archiving computers, the next one. So these archiving computers are going to tell us the data in the historical data, or say for example last month what is the production, or last month how the process taken place, or the temperature level in the last year, how much it was for the month number 1, month number 2, month number 3, or different parameters like pressure, flow, position, all those things, data, whichever the required data, these data can be stored in the archiving computer. Say for example, if you take a renewable energy system, if you have a solar based power plant, so this solar based power plant is producing the electricity from the solar power, and this solar power each and every month it is not going to be same. Say for example, you have January, you have different temperature, pressure, humidity, and all those things, and in May or June it will be different. And so when the month is changing, then the temperature and all these parameters also changing. So for throughout 1 year it is producing certain amount of power based on the light availability and other parameters like temperature and pressure, all those things. So this will give you the historical data for one particular year, in which month how much temperature, how much speed, pressure, humidity, all those things, and how much power is being produced, and how much power is being utilized, and how much losses are there, how much different type of fault is, faults, what are the different type of fault we got in that system. So all these data can be put it in the archiving computers. So it will be used for us to predict the future power production, and it will be used for predicting the maintenance work and things like that. So this is the purpose of having the archiving computer. So this archiving computer will give the data for analyzing purpose, and also it will be used for predicting the future power production or whatever it is, so based on your plant. So it is archiving computer is nothing but a storage computer which will have a different information about different years, and based on the parameters which you need to control or which you need to monitor. So based on that, the data will be stored here, and it will show the graphs as well. So how the trend goes from one year to the another year. Say for example, if we have a production plant, how much power is being, how much product is being produced, how much is the sales, and how much is the rejection ratio, and the time for producing the particular product. So all these data can be put it in a graph, and you can easily see whether you are progressing or you are having an issue in improving your system. So this is the purpose of having archiving computers. Then the next one is a designing station, as I told you here. So the designing station is used for configuring the PLCs or the controllers, which is used to control the field devices, and which is used to give the input to the servers and operator station for a future purpose. So in the designing station, they design the PLC programs, hardware settings, and most of the things like that. So these PLC logics, or if you have any other dedicated controller, so based on that, okay. So I'm just telling you the example PLC logics, and also it is used to create a graphical displays in the operator station. So what actually the operator station should show, what are the parameters should be monitored, and things like that. And network setups, so this is very important. So we have to connect this all system through network. So the what kind of a networking system is there, and what is the speed, and what are the devices and security systems, all those things will be designed from the designing station. So overall, the designing station will have this works: hardware configuration, PLC logics, creating graphical displays, network setup, all those things will be done in the designing station. And I already discussed about the server. So this is the overall system. If you see the overall system, it looks like this. So we have operator station, we have server, archiving computer, designing station, we have controllers, and then we have HMIs here, and then we have field IO modules, and then we have field devices. So as I told you earlier, so the designing station is going to have the PLC programs from there, and it is going to be distributed to the different PLCs here, and then the graphical displays, whatever the graphical displays which we need for the operator station, also designed from here, and it will be transmitted or sent to the operator stations. And the network setups, whatever the network setup we have from the controller to server, archiving computers, and controllers to field the input output module, and things like that. So all these data will be sent from the controller, this one designing station, to various components, and also it will give the inputs to the HMIs, input HMI, human machine interface devices. So these points already we have discussed. Components of DCS. Controllers. So we can have a different type of controllers: single loop controllers, multi loop controllers, advanced process controllers. So single loop controllers, as I told you earlier, so it may take only one variable, and based on that one variable and preset value, it is going to monitor that particular variable, and it is going to perform the task. So these are the simplest of all type, and they use a single input and a output channel, and are typically used for basic control tasks such as flow rate, temperature, pressure controls. An example of single loop controller is a proportional integral derivative or PID controller, which adjusts the output based on the error between desired setup point and measured process variables. Components, again, the multi-loop controllers. These type of controllers are capable of controlling multiple process variables simultaneously. They have several input and output channels and can handle complex control tasks. Multi-loop controllers are often used advanced control elements and algorithms such as model predictive controls or adaptive control, or optimize the performance of the system. The third one is advanced process controller. These controllers are designed for even more complex control system or functions and can handle multiple inputs and output as well as non-linear and time varying process. This is important. These controllers have subsystems. Sorry, these systems have subsystems and use sophisticated algorithms such as artificial intelligence, machine learning techniques to optimize the control performance and adapt the changing process conditions. Example of advanced process controllers include neural networks and fuzzy logic controllers. So now let us come to the controller part. So where the controller will have the programs, PLC programs or the controller program, and also it is connected to the human machine interface. The controllers are connected to the field IO module and the field devices, and then it is also connected to, as I told you earlier, it is connected to the server and archiving computer, and it feeds the input to the operator station as well. The PLCs, the controllers will have the redundant CPU and the primary CPU. Two CPUs will be there. In case of a normal operating stage, the primary CPU will perform the task and it controls the variable parameters in the field devices, and it feeds the data to the required places. In case of the primary CPU fails, then the redundant CPU will do the task. So it will not stop. Actually, the primary CPU, if it is fails, then the process will not stop. The redundant CPU will perform the task that time, and in the same work will be achieved in the process through the redundant CPU, and it will communicate to the required devices in the required way. In case if the primary CPU and the redundant CPU both fail, then the process, that particular process stop working, but the remaining process, whatever is ongoing in the field or the plant, it will be not affected and it will do the function. This is a difference between the centralized and decentralized control unit. So since you have a different controllers for performing different tasks, so if one particular task is not done or achieved because of the failure of the process controller, uh, the other process will not get affected until otherwise it is interlinked. So these processes can perform the task without having any problem because of the first controller or first stage. So this is the overall picture of the system what we discussed until now. So the controller gives the input to the server, and it gives to the archiving computer, and it gives to the operator station, all those things. HMI, human machine interface. So this is at the controller level. So where the operator, the field operator sets the parameters and watch the operations, and then in case of alarms he resets the value, or he changes the parameters, things like that. So this is at the supervision and command at the controller level to closely monitor the process at the particular field, a particular area. So this human machine interface is very much helpful to closely monitor the system. So this person we can monitor only this particular task. So he cannot monitor the second stage or the third stage which is happening at a different place, but he can monitor only the process which is taking place by this PLC and this particular control devices. A human machine interface or operator station provide a graphical interface for operator to monitor and control industrial process. HMI enables operator to visualize process data, interact with the DCS control algorithm, and perform various tasks such as adjusting set points, acknowledging to alarms, and initiating manual control actions. Let's indulge in the detail of all the functionalities of HMI. So it has graphical representation of process data, very much useful because the person who is at the operator stage in the controller level, so he must be easily understand what is happening. So that's why the graphical representation is always used. Control and monitor function, control and monitoring the functions. Alarm managements. So if the process is completed, or the set points are crossed, or different kind of alarms can be monitored. Historical data analysis can be done. Security and access control can be also achieved in the HMI systems. So in a graphical representation, so we have the HMI displays process data in a user-friendly format using graphical elements such as trend, bar graph, gauges, things like that. So the gauges may show the pressure gauge, pressure, temperature, and different kind of variables. And this allows operators to quickly understand the current status of the process and identify any deviation from the desired operating condition. So this is the work of him. So he must be, say for example, if the temperature is to be monitored, so he will keep watching this HMI system, and he will see whether the system works within the set temperature. In case if any deviations is there, you can change or you can modify the input parameters. Control and monitoring functions. HMI provide various control and monitoring functions enabling operator to interact with the control system. These functions including adjusting set points, initiating manual control actions, and acknowledging alarms. By providing a centralized interface for control and monitoring, HMI improves the efficiency and effectiveness of the plant operation. Alarm management. So alarm management is a critical aspect of HMI design, ensuring that operator receives timely and relevant information about abnormal process condition. HMI displays alarm in a prioritized manner, allowing operator to quickly identify and address most critical issues. Advanced HMI system also provide features such as alarm filtering, grouping, suppression, helping operators to manage large number of alarms effectively. So also it is used to give the historical data analysis. HMI often include data historian functionalities, enabling operator to analyze historical process data and identify trends, patterns, anomalies. This can be useful for troubleshooting, process optimization, and decision making. Security and access control. Modern HMI incorporate security features in the management system such as user authentication, access control to protect the control system from unauthorized access and potential cyber threats. By implementing role-based access control, HMI ensures that operator can only perform actions within their designated authority. So he cannot modify every parameters, only few parameters which he can monitor and he can control, only that will be authenticated. Remaining parts we will not have the authority. HMI can be implemented on various platforms ranging from dedicated hardware panels to software applications running on standard computers on or mobile devices. The choice of HMI depends on factors such as the complexity of the process, the required functionality, and the environmental conditions. Remote I/O, that is input output modules. So these modules are used to connect the PLC or the controller and the field devices. So these input output modules can be of a digital or analog or different type of input output modules. So the purpose of these input output modules are to connect the control room and the field devices such as sensors, actuators, and other process equipments. Input output modules are responsible for collecting data from the sensor and converting it into digital signals and transmitting into the controller for processing. These input output modules actually, if it is analog signals or digital signals, whatever it is, but the controller can understand only digital format. It is not going to understand anything in the analog format. So these input output modules takes the various inputs. Say for example, some sensors gives 4 to 20 milliampere current outputs. Some sensors gives a different type of voltage outputs. So different outputs are coming from the sensor. So all these data which needs to be collected from the sensors, and it should be readable and understandable from the controller. So this is the role of this input output module, collecting the data and converting into understandable template or format by the system, and it will send it to the field devices. Similarly, when it is returning back, to the field devices, the controller gives the digital inputs and it will be converted into required format. If it is analog, it will convert into analog, or if it is a digital, it will be sent as a digital, and with a required voltage and current levels. This is very important. Required voltage and current levels it will send to the particular field devices. This is the input output module purpose. So as I told you, it can be of analog input modules or analog output modules. The analog input modules handle continuous signals from sensors such as temperature, pressure, flow measurements. They convert analog signal into digital values using A to D converter and with a specific resolution, typically ranging from 12 to 24 bits. Analog output modules. Analog output modules are used to control via valves. So this is the output part. So once you take the input from the input sensor according to the program and the set values, so it needs to give the output to the output devices like valves, motors, pumps by generating the continuous control signals. They convert digital signal from the controller to the analog signal. So using a D to A converters. So it can be also a digital input modules where you get the digital inputs. Digital input modules are designed to handle discrete signals from devices like switches, relays, binary sensors. So if you have a conveyor control, whether the object is crossed or not, how many objects are crossed. So all these data are like a digital inputs. Okay, so each time one object is crossing, so it will make a count. So based on that, it will do the other works. So whether you need a five objects to be placed in a box, or how many objects is being produced, or how many are rejected. So all this can be done using sensors which will count the devices. Digital output devices. These modules control discrete devices such as solenoid, valves, contactors, indicator lights by generating discrete output signals. So this is on-off controls. It's like you open or close the valve, or relays can be on and off. The indicator lamps can be on and off. So these are digital output modules work controlling these digital devices. So input output modules can be further classified on the communication interface such as serial parallel or field bus protocol. Some common field bus protocol used in DCS include ARPANET, HART, Foundation Field Bus and Profibus. These protocols enables efficient communication between input-output modules, controllers and other system components, ensuring reliable data transmission and real-time control. So this communication is very important because all the data from field devices and archiving computer and server and to the operating station, all those things are communicating through this communication networks. If the speed of the communication network is low, or if it is erratic, then it will not be efficiently controlling the total process. In addition to the basic type of input output modules, there are specialized modules designed for a specific application, such as temperature input modules, which handle signals from thermocouples and RTD kind of sensors. These modules often include additional features such as cold junction compensation and linearization to ensure accurate temperature measurements. The selection of appropriate input-output module depends on various factors including the type of field devices, signal characteristics, communication system requirement and environmental condition. By choosing the right input-output modules, industries can ensure accurate data acquisition, efficient control and reliable operation of their DCS. So field devices, so this can be of anything. So it can be of a switch, or it can be of a valve, or it can be of a motor which is connected to the contactors, or it can be of any analog sensors. So many devices are there in the field devices. So components of DCS, the communication network, as I told you, this is very important part of a DCS system, because the DCS is not centralized system, it is a decentralized system. So the process taking place at different areas of a plant. So the data needs to be collected and it needs to be timely processed, and it has to be action taken at a required points. So the communication should be faster, safer, and error free, and it should be user friendly as well. So these are the importance of the communication networks. So these networks ensure reliable and real-time communication, which is essential for maintaining efficient and safe operation of industrial process. This is what I said. There are several type of communication networks and protocols used in DCS, each with its own characteristics and advantages. Some common communication protocol includes HART, highway addressable remote transducers, foundation field bus, Profibus, that is a process field bus, industrial ethernets. So let us see what is a HART, or highway addressable remote transducers. HART is widely used communication protocol for process automation. So since it is a process automation, that's why we are going for a DCS. So it is very much helpful to use a HART type of communication networks, combining analog and digital communication over a single 4 to 20 milliampere current loop. This is the advantage. This allows HART devices to transmit both process variable data and additional information such as device diagnostics and configuration data. HART is compatible with existing analog instrumentation, making it a popular choice for advancement in legacy control system. Foundation field bus is a digital bidirectional communication protocol designed specifically for process automation. It provides high-speed communication, deterministic data transmission, advanced features such as device diagnostics, multivariable measuring capability, control in the field and network redundancy. Foundation field bus enables the integration of multiple devices and functions on a single network, reducing wiring complexity and improving system flexibility. Profibus is widely used industrial communication protocol supporting both process automation and factory automation. So process automation is achieved using Profibus PA and factory automation is achieved using Profibus DP. Profibus provides high flexibility because of its modular structure, high speed, quick data exchange, and support a wide range of devices such as sensors, actuators, controllers, and HMIs. It also offers advanced features such as network diagnostics, device configuration, and redundancy. Industrial Ethernet is a variant of a standard Ethernet protocol adapted for adapted for use in industrial environment. It offers high-speed communication, real-time data transmission, robustness against electromagnetic interference, and harsh environmental conditions. Industrial Ethernet can be used with various protocols such as Ethernet IP, Profinet, and Modbus TCP or IP, providing a flexible and scalable solution for DCS communication. When designing a communication network for a DCS, several factors need to be considered such as the required data transmission speed, network topology, and environmental conditions. So applications, so it can be used in power generation, oil and gas, water treatment plants, pharmaceutical and biotech, manufacturing, also in infrastructure. So these are few examples. It can be used anywhere where you have more complicated process. Power generation, DCS are used to control and monitor power generation process such as coal-fired, gas-fired, nuclear power plant. They are used to control, monitor the process variables such as temperature, pressure, flow, and level to ensure the safe and efficient operation of power plants. Oil and gas, DCS are used to control and monitor process in the oil and gas industry such as drilling, refining, and petrochemical production. They are used to control and monitor the process variables such as pressure, flow, level, and to ensure the safe and efficient operation of process. Water treatment plants, DCS are also used to control, monitor process in water treatment plants such as water purification, desalination, and wastewater treatment. They are used to control and monitor the process variables such as flow, pH, and temperature to ensure the safe and efficient operation of process. Pharmaceutical and biotech, DCS are used to control and monitor process in the pharmaceutical and biotech industry such as fermentation, distillation, and purification. They are used to control and monitor the process variables such as temperature, pH, and pressure to ensure the safe and efficient operation of the process. Manufacturing, DCs are also used to control and monitor process in manufacturing and assembling lines, robotic systems, and packaging systems. They are used to control and monitor process variables such as temperature, pressure, flow, and level to ensure the safe and efficient operation of the process. Infrastructure, DCS are also used to control and monitor process in infrastructure such as traffic light control system, building automation system, transportation system. They are used to control and monitor process variables such as temperature, pressure, flow, level to ensure the safe and efficient operation of the process. Fossil fuel power plants. In fossil fuel power plants such as coal, natural gas, and oil fired plants, DCS controls fuel handling, combustion, steam generation, and turbine operation by controlling variables such as temperature, pressure, and flow. DCS helps power plant operators to optimize fuel consumption, reduce maintenance cost, and improve overall plant performance. Nuclear power plants. In nuclear power plants, DCS is used to manage complex processes involved in nuclear fission, heat transfer, and electricity generation. DCS provides real-time monitoring and control of critical process variables such as reactor temperature, pressure, and neutron flux. DCS also plays a crucial role in managing safety systems such as emergency cooling and contaminants, as well as radiation monitoring and protection. Renewable energy system, DCS is also employed in renewable energy power plants such as hydroelectric, solar, and wind power plants. In hydroelectric plants, DCS is used to control water flow, turbine operation, and generator outputs. In solar power plant, DCS manage the operation of solar collectors, inverters, and grid integration. In wind power plant, DCS is responsible for controlling wind turbine operations, including pitch and yaw control, as well as monitoring the performance of individual turbines and entire wind farm. In renewable energy power plants, DC is also employed in renewable energy power plants such as hydroelectric, solar, and wind power. So this is already we discussed. So these are the fundamentals or the basics of DCS. Each and every aspect of it needs a lot of information to be discussed and analyzed. So I just try to give an overall view of a DCS, distributed control system, and where it is used and why it is used, what are the different parts of it, and how it is going to be different from other control system like a PLC based control system. Is there any difference between them, or both can perform the same task? So that part we will discuss in the next video or the upcoming video. So that is about the difference between PLC based control system and DCS based control system. Hope you understand the concept of a DCS, distributed control systems. In case if you have any doubts, please let me know. And I am also in a learning stage for the DCS systems as concerned. So if you know, also you can share a few points which maybe I have missed out, or the additional values or the additional points which you want to discuss or share with me. Please give the feedback to the comment box. So let us learn together. Thank you so much.